All right, let's start. Once again, final exam, Wednesday, December 13, 10:30 a.m. Same place, same location, within the hall. Make sure you know where to go. If you get lost, look for your TA or look for me. All right, let's start. The first thing I want to do is, last time I said we would start with Newton's law of cooling problem. So let's start with one. In this problem here, we have a cup of coffee that was brewed at 130 degrees. It is left in a room with a constant ambient temperature of 70 degrees. 4 minutes later, after we put it out, the temperature of the coffee dropped to 120 degrees. We'd like to find out how long we have to wait from the time we leave it in the room until it drops down to 100 degrees. The equation says the rate of change of the temperature of some object is proportional to the difference between the temperature of the object itself, T, and the surrounding temperature, Ts. And that Ts is always assumed to be a constant. And T, capital T, of course, is the temperature of the object, in this case, that cup of coffee, and little t is time. Okay? Yeah. It's just like the K in the standard exponential. Yeah. It's very similar in structure to the standard growth or decay equation, Ky. That K, those two K's are the same kind of things. Okay, so let's solve our problem here. Our goal, we know how to solve this one, the second one, the standard equation. We know it's equivalent to y of t is equal to y of 0, e to the kt. Then we find k and then we solve our problem. We can turn the Newton equation into this one. So in the Newton equation, if you make a substitution, let y be capital T minus Ts. Then dy dt, d little t, is the rate of change of d capital T. And because Ts is a constant, it has no derivative. Okay? So if we make this change here, then notice what happens. This equation can be turned into d capital T dt is the same as dy dt. And the right-hand side is k times t minus Ts. But we're calling that thing little y. Therefore, what you have done here is you turn the Newton equation into a standard growth and decay equation. And in this case, y is t, big T, that's a function of time, minus the constant Ts. Okay, so then we know this and that are related. Y of t is equal to y of 0 at t equal to 0, e to the kt, which, using this definition of y, we get t of time minus Ts. Right? That's a y of t. Right-hand side is when little t is equal to 0. big T of 0 minus Ts e to the kt. So that equation in the box and on the lower right corner, that's the equation we're going to need to solve this problem. The steps are the same. We find out K. Once we know K, we can find out the temperature at any future time. Okay, any questions so far? Okay, so all we did is we took advantage of this. You have to know this. We'll give you this equation, the cooling equation here. If you need it, we'll give it to you. But you have to know this. We won't give you these two equations. You have to know these two, the standard growth decay equation. Now we have this equation in the box to work with. Let me rewrite it. Now we can say that capital T, temperature of the coffee, I'm going to add that Ts to the right-hand side. Now this equation just gives me the temperature of the coffee at any future time. Once I know K, that's all I need. The problem gave us Ts, the ambient temperature, the surrounding temperature of the room at 70 degrees. Right? The problem gave us the initial temperature of the coffee. Temperature T at T equal to 0, 130. We also know from the problem that 4 minutes after I left it out in the room, the temperature dropped to 120. I started with 130. 4 minutes later, I got down to 120. So this is what I know. That equation now, putting the Ts value, we get 70 plus initial coffee temperature, 130, minus the surrounding temperature. So we get 70 plus 60 e to the kt. Okay, now we find K using the information that 4 minutes later, temperature is 120. That's the future temperature, goes on the left. Took 4 minutes, so K times 4, or 4K. Now we can find K, right? Subtract 70. Divided by 60. Take the natural log, all the standard stuff. Solve for K. And we can write K as 1/4 ln of 5 over 4, or ln of 5 over 6, to the power of 1 over 4. Okay, now we take this value of K, plug into that equation, and rewrite it. 70 plus 60 e to the K to the power of T. Like we did last time, I'll write e to the K in the brackets. And the reason is because e to the natural log of whatever can be simplified to just whatever that thing is. E to the ln of that is equivalent to just, in this case, 5/6 to the power of 1/4 raised to the power of t. Okay, now I found K. This equation will tell me the temperature of that cup of coffee at any future time. The problem wants us to find the time it takes for the coffee temperature to drop down to 100. So we want to find ultimately when capital T is 100, what is the corresponding time? And that's easy. I put in my temperature. Subtract 70. Divided by 60. Natural log of both sides. Okay, I brought down the T/4 once I took the natural log. And then so it's natural log of 5/6 times that power. Now I can find little t. Very simple. I divide it by natural log of 5/6 and multiply by 4. Okay. Now on the exam, if this were a question on the exam, obviously you can't figure out what natural log of 1/2 and natural log of 5/6 are. So the answers will have these things in them. You just have to choose the right one. But if you actually were to calculate this turns out to be about 15 minutes. Roughly 15 minutes. Again, that's the part that without a calculator you won't be able to find. But you could get this far here. Okay, so that's a very typical Newton's law problem. The idea is Newton's law of cooling problem. You turn it into the standard growth and decay, use that equation, and you do the same thing you would always do. Find K, and then once you find K, anything else can be found from the resulting equation with K known. Questions? No? Good. All right, let's carry on. Last time we ended with 19. Let's go look at 20. 20, we're looking for the derivative of the definite integral from 1 to 2x. Radical t squared plus 1 dt. So this we have to turn to the first version of the fundamental theorem of calculus. FTC1 says the derivative of the integral from a constant a to some variable x of some curve as a function of t is the same as whatever that curve is as a function of x. And remember, if the limit there is not x, then we have to use chain rule. And that's the situation we got here. Okay? All right, so to organize this better, let's call that integral y for the moment. And I noticed that the upper limit is not just an x. So FTC1 does not directly apply. We got to do an intermediate step. Okay, so if we call 2x u, then right now we got y is equal to the integral from 1 over u, 1 to u, radical t squared plus 1 dt. The derivative of y with respect to x by the chain rule is dy du, because y is immediately a function of u. And then we chain it together by multiplying the derivative of u with respect to x, the variable that we're really interested in. For dy du, we can use the fundamental theorem of calculus directly, because it's now just changing x to a u. Dy du will give me radical u squared plus 1. And then du dx is 2. And finally, we get 2 times radical of u squared, but what's u? U is 2x. All right, so that's the derivative of that integral from 1 to 2x and so on. Oh, and the problem wants us to find this thing at x is equal to radical 2. Well, that's easy. That part is trivial once you got this equation. So what's this? It's 4 times 8. 8 plus 1 is 9. So that's a 3 times 2, 6. Okay, so you have to know this, and you have to know what happens when the variable is not just an x, but something more than just an x. You also have to know what happens if the variable part is at the bottom. In that case, you're going to swap it first. Flip the sign. Yeah, that's right. And then you can apply FTC1 potentially with chain rule. Any question on this one? Yeah. Correct. If this were just an x here, then I simply use that. There's nothing more I needed to do. But we did all these extra things because that's not just an x. All right, 21. Definite integral from 3 to 4, x radical 25 minus x squared. Let's rewrite it. Okay, now if you look at this thing here, you should be able to recognize these two parts as being related by a derivative. And when that happens, then you know we must be dealing with something that requires a substitution. Derivative of 25 minus x squared is minus 2x, which is minus 2 times x, right? And so that's a clear sign that you want u to be 25 minus x squared, and then you integrate. We integrate by substitution with u is equal to 25 minus x squared. And also be very careful with the integration limits. Those refer to x. Once we go to the u world, we have to make sure these reflect that change. Okay, one thing at a time. First, we know we made a choice to let u be that thing. The next step is to find the differential, du. And now let's adjust the limits. Yeah. You could do that, but this is more direct. That's fine. You can go back to x and leave the limits alone. Either way is fine. I just think this is more direct. Change the limit to u and then finish the problem in u. Whatever you prefer. Okay, so the upper limit used to be x is equal to 4. That now, according to the u equation, is 25 minus 4 squared. So that's a 9. The lower limit used to be x is equal to 3, but in the u world, it's 25 minus 3 squared, and that's 16. Okay, so let's change things out. 3 turns into a 16. 4 turns into a 9. This guy is u to the 1/2. And then x times dx, minus 2x dx is du. If we just have x dx, then that's negative 1 over 2 du. So here we have an upper limit that's lower than the lower limit. That's a very, very typical thing once you got substitution involved, and there's nothing wrong with that. Nothing wrong whatsoever. You just integrate the normal way. The constant multiple of 1/2 doesn't do anything. For u to the 1/2, we add 1 to the old power divided by the new power. And then we'll plug in 9 for u and then 16 for u. Next. This is dividing by a 3 over 2, so you're right. We're multiplying by the reciprocal, so that's 2 over 3. And that'll turn into negative 1 over 3, actually. Okay, so now we're putting u, 9 for u first. Watch the signs. This is what the thing would be if u is equal to 9. Subtracting away the same thing, including that negative sign, with u equal to 16. All right, so now 9 to the power of 3 over 2 is, take the radical first, you get 3. 3 cubed is 27. So that's what we get. This turns into a plus. Same thing here. 16 with a power 1/2 is 4. 4 cubed is 64, is that right? So what do we get? We get 37 over 3 or something? Right. Okay, so there it is. Questions? All right. Moving on, 22. It's a limit to infinity problem. This one seems pretty short. That's 1 over 3. You're right. It's very simple. Remember with this one here, because you're going to infinity, these guys have the same powers. And when that's the case, then you're going to divide it by the coefficients. Limit is the ratio of the coefficients of the leading terms. So we get 1 over 3, right? Alternatively, this thing goes to infinity over infinity, so L'Hopital's rule is another choice you could go with. All right, so that's a simple one. Nothing really to talk about there. Next one, limit goes to 0. 2x minus the inverse sine of x over 2x plus tangent, inverse tangent of x. And this looks like a L'Hopital's rule problem, because when x goes to 0, that's a 0, and then inverse sine of 0 also happens to be 0. Downstairs, when x goes to 0, that's a 0. Inverse tangent of 0 is also 0. Okay, so because we got infinity over infinity or 0 over 0, we can use L'Hopital's rule. It doesn't seem like we have any other choice, so that's what we'll do. Take the derivative on the top. We get 2. And what's the derivative of inverse sine? You remember? 1 over what? Root 1 minus x squared, correct. Downstairs, derivative of 2x is 2. What about the derivative of inverse tangent? All right. Okay, now you let x be 0 and see what happens. So we get 2 minus 1 over 1. Downstairs is 2 plus 1 over 1 because x is 0. So we get 1 over 3. Huh, these two have the same limits. Cool. Any question? Let's continue. 24. We got we're told that f double prime is positive for x is less than c. We're told that f prime of c is equal to 0. And we're told that f prime of x is less than 0 for x is greater than c. And we have 5 of these to choose from. I'll just roughly sketch each one of them. And D looks like this, and then that. And that happens at C. And finally, E is the same as C, but upside down. All right, so now you just have to make sure you understand each of these three and then match it up. The first one says that f double prime is positive for x is less than c. It means that the graph should be concave up, right, for positive second derivative whenever x is less than c. Second one says that f prime of c is equal to 0, means tangent line is horizontal at x is equal to c. And the last one, f prime is less than 0, means the function is decreasing. If x is greater than c. The first one alone can eliminate quite a few of these. You want concave up for anything to the left of c. That's concave down, right? So that's not right. That's a concave down here. We don't want that. Concave up, possibly, 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 and not this guy, because that's concave down. So first statement rules 2 of these out. Tangent line wanted to be horizontal. We have possibly, possibly, yes, yes, possible, no. This is not differentiable. F prime does not exist. It's not differentiable when there's a corner or a cusp like we got here. So now we're down to B and C. Last one says we want this to be decreasing for x is greater than c, right? That's increasing, that's decreasing. So that guy is not right, because this one here is increasing. So there's our choice, B. All right, that seems pretty simple. Questions? $25. Oh, this one sounds interesting. Let R be the region between the graph of between y is equal to 1 over x and the x-axis. From x is equal to a to x is equal to b. And And all that says is that B is bigger than A. If the vertical line x is equal to C cuts R into two parts of equal area, then C is equal to. We're looking for a number somewhere between A and B such that we cut this area into two equal halves. C is a number between A and B. Find C where x is equal to C such that R, so let me sketch this out. Here's R1 over x. Let's say this is A. Let's say this is B. Okay? And let's see, by eyeballing that, it looks like C is probably somewhere over here. So let's first find out this entire thing. The area of that region R is the integral from A to B of 1 over x dx. And we know this is natural log of x, AB. So that's natural log of B minus natural log of A, or natural log of B over A. Either way is fine. And now if we want to, this C here is supposed to chop this into two equal halves. So each of these two halves is going to have an area of 1/2 of natural log of B minus A, because natural log of B minus A is the entire thing, right? So knowing this, I can do the same thing. The area from A to C underneath 1 over x dx is natural log of x AC, which is then natural log of C minus natural log of A, or natural log of C minus A. Now, knowing the fact that this thing is going to have an area that's exactly 1/2 of the whole thing, we know this has to be equal to 1/2 of the entire thing. Right? Does that make sense? Yeah? Okay? And now we just have to find out C, right? Yeah, there are a couple ways you can do this. We can say natural log of C over A is equal to natural log of B over A to the 1/2. So we have natural log of something equal to natural log of something else. That can only be true if C over A is equal to that B over A to the 1/2. If they have the same natural log, then they must be equivalent. So this tells us C is equal to A times B to the 1/2 over A to the 1/2. So that's going to give me A to the 1/2 times B to the 1/2, or radical AB. All right? Okay, 26, the area of the region between y is equal to 1 over x, 1 plus x squared, and the x-axis from x is negative radical 3 to x is equal to 1. Yeah, it's just an integration, you're right. We want the area between that and the x-axis from this to that. So that's a definite integration from left to right underneath 1 over 1 plus x squared. And we saw this before. This is a derivative of an inverse tangent. So when you integrate that, you get inverse tangent of x. And therefore, we get inverse tangent of 1 minus the inverse tangent of negative radical 3. And now it's just a matter of knowing these two values. Inverse tangent of something positive, that's a first quadrant angle. In a first quadrant angle, what angle has a tangent of 1? Pi over 4, right. Inverse tangent of a negative number, that's a fourth quadrant angle measured clockwise. So in the fourth quadrant, what angle has tangent equal to negative radical 3? If it doesn't look familiar, look at it as negative radical 3 over, rather, put a minus sign here. Think of it as radical 3 over 2 over 1 half. Right? So we want the sign to have a radical 3 in the fourth quadrant, counting clockwise, and that's pi over 3. Negative pi over 3, is that right? So that's pi over 4 plus pi over 3, 7 pi over 12. Yeah. I'm sorry? Minus root. Right, what about it? Because the range of the inverse tangent function is minus pi over 2 to positive pi over 2. So it's the fourth quadrant, but you have to look at it as something that's negative, a negative angle, as opposed to going all the way around to the fourth quadrant counterclockwise. Other questions on this one? All right, 27. Looks like a not. Well, that's a derivative problem. What's it doing here? Okay, it's actually a good thing to look at here because when you have natural log of something, there is often a chance to simplify what you have to deal with. And so you can use the product rule the way it is right now. There's nothing wrong with it. However, you could make things a little bit easier for yourself. Remember, with natural log, you can always move the power to the front. So if I do that, then when I take the derivative of the second part here, now I have something that's slightly easier to deal with. Instead of natural log of something to a fractional power, it's now simply a number times natural log of something much simpler than it used to be. So let's apply the product rule. Here we get first times the derivative of the second, 1 over 2, times 1 over 1 plus x, times derivative of 1 plus x, that's a 1. Right, so you can see in this step here, if I had done the same thing with this expression, equivalent expression but looks different, then the chain rule part would be more complicated. The 1 here would be derivative of that, and that's of course more complicated. First derivative of the second plus the second times derivative of the first. So e to the 2x times another 2. And all that's left to do here is simply simplify just a little bit. E to the 2x over 2 times 1 plus x plus e to the 2x times natural log of 1 plus x. Okay, so on the exam, if you see something dealing with natural log, especially when the natural log expression is complicated, look for ways to simplify the natural log expression before you do anything to it. It'll be better to handle simpler natural log, potentially more of them, but that's okay. Each one is simpler, that's always better. All right, I think we got time for one more here. So we won't be able to finish this, and what I'll do is I will write up the solution for the ones that we didn't get to in class, and then upload them. But that'll probably be this afternoon, because like I sent you an email last night that I'm teaching for Professor Gabrielov today, so this morning I won't be able to upload the rest of the solutions. But this afternoon I'll make sure I upload the ones I didn't get to. Sound good? Okay. So where were we? 28. 28, looking for the derivative of x to the power of sine of x. This was on exam 2 or 3, wasn't it? All right, that's fine. Okay, so we got a complicated thing going on in the exponent. We don't want that. So we take the natural log to get it out of the exponent. Now we take the derivative on both sides. Left side is 1 over y, but then chain rule applies. We need to multiply by y prime. Right-hand side is a product rule. First times derivative of the second plus the second times derivative of the first. Now we want y prime, so let's multiply y to the right-hand side. No. The limit of that is 1 as x goes to 0, but by itself it's not. Then y is equal to this thing. So we change it back out. And there we go. Okay, so I'll finish the rest. Maybe this morning I might have time to do it, but if I don't, then by this afternoon I'll have the rest of the solutions worked out. All right, don't forget the exam, Wednesday. Next week, I plan to hold my Monday office hours as usual, but not the Wednesday office hours. Because guess what? We'll be taking an exam on Wednesday. So Monday, I'll be there 9 to 11, okay? All right, see you Wednesday.